All right, another day, another coding challenge. This stream is for entertainment purposes only. Let me quickly check if everything is working fine. All right, seems like that. So, today as usual, we're gonna try to solve some coding problem under 40 minutes, hopefully. If it's not hard, if it's hard, then unlikely, but yeah. Let's see what we've got today. Pick one. All right, it's medium, it's linked list in binary tree. Nice. So I already see how we should search binary tree in linear time. Given a binary tree root and linked list with head as the first node. Return true if all the elements in the linked list starting from the head correspond to some downward path connected in the binary tree. Otherwise, return false. So we have root and we have head as the first node. Okay. Then true if all of the elements in the linked list starting from the head correspond to the. So are we giving BST? I didn't get. Is it binary search tree or is it just a arbitrary binary tree? So it's okay. So basically, we spent, my understanding, linear time to find the first element. I mean, to find the head within the root tree. And once we did it, let's say we can use breadth for search or whatever. Once we hit it, from this element, I guess we were only allowed to take the childs, right, of that one. I see. Yeah. I don't really know if we need to clarify any algorithm here. To me, it sounds super trivial in a sense that, yeah, we have next, and basically that's it, right? That's all we need. Basically, every time we had next until we hit the now pointer. So the first example, right? So we finish somewhere here, and it's true. All right, yeah. Super easy. I don't know. All right. So we start with breadth for search. So we're basically searching for the head. And once we found the head, all we do is just go through every element in the head and check if one of the childs is this. If not, we break, right? I see. So ideally what we want to do, like in this case, right, we have 4 and 2. So we put in the queue 4 and 4, right? So we take first element 4 and it matches with the element in the list. So we start going through elements in the linked list. And if next one is the child of list, then we put it in the queue. If not, we return back to the head, right? We don't put it in the queue. We don't need to put it in the queue. We just go through the all children's. If we hit the end of the list, we return true. If not, every time, by the way, we hit the new node, we add those childs in the queue that are not on the pass, right? Like in this case, we go 4, 2. We don't add neither 4 nor 2 back to the queue, but we add 1 because we have no idea if there are any other paths beyond it. And then if we stuck with the list, we just break and return back to the queue. Okay, sounds easy. All right, so let's see. We have queue of 3 node called queue. So is it push? I always forgot. So there is a difference between queue and priority queue. Either, I guess it's push, right? Then we have list node next, or let's call it next list for, and then it's basically head. And while empty not, so we do this. We can use auto next tree, right? Next list, next tree. Yeah, maybe naming is not the best here. Equals queue front. Then we do queue pop. Is that the API? Let's go with this one just in case. So if next tree value we don't need next list here. We need it within if block here. If next tree value equals head value, right? Traverse list. So do something. Come on, do something. Else, so if it's not, then we just say queue push, right? Root we need to say, all right, we don't want to push null pointers, right? So queue it's not a root, it's by the way next tree. What left? Let's start with left equals null pointer, not equals null pointer, or not, although I like more explicit way of saying it's not null pointer. We push next tree left to the queue. Same for the right. All right, so this is simple. By the end, by the way, at the end we return always false. So if we were unable to find anything and traverse the entire tree, so we just return false. All right, so now we need to do something to traverse the list. So how on earth we traverse the list? we say next list head here, right? And while next list let's say not equal no ptr, right? We do something. No, let's say differently. Or should we? So we need to, so we know head, actually we can say next, right? Next, we don't need. So we start with the next element in the queue. So because the current element, so we need to check that the next element is either right or left. So we check if next list value all right, so we do to check also for now pointer here. No, not like next list. Next tree, if the next tree element has the left child, the right child, the left child, and the next list value equals to next tree left value right, so we have left child on the tree, and next list is okay. All right, so next list equals to next list next, right? So we're moving to the next element, next. Then we also need to add the right element to the queue if it's not now, right? Next tree right element. So because it's the left element, right? We push its right child to the queue, and what do? We say that next 3 is equal to next 3 left. All right. Else, if basically same stuff, but now for the right, and we say it's right value is equal to right and then we basically do exactly the same thing, but now for the right element. So let's do next. So because it's equal to the right value, to the right child, right, we say push left to the Q, not right, left now. And next tree is the right. So we're moving to the right. All right, so after this cycle, right, so okay, else, so if it's neither left or right, else do not match the downward path. So what do we do if it doesn't match? So basically we hit this 8, right? Oh, let's say in this case, let's assume that was not 8 by itself. We hit 2, right? Currently 2. So we do two things. First of all, we put both left and right to the Q because they're potential solutions to the pass. Then what we say? Then we say that, okay, next list we will reset it, obviously, right? So we break from this internal while cycle, and at the end of this while cycle we check if next list is null pointer. We return true, right? So we don't need to do anything after that. So this is it. This is the entire algorithm. So what's the logic here? Let's assume on the example 1 that this is not 8, this is 7, right? So it doesn't match. We start with 1 here. We pop 1, we go, let's assume this is 3, so we never, so we say 3 and 4. Okay, 4, we match with the head, right? So for the 3, we just put 2 in the queue. So in the queue we have 1, 4, and 2. And let's assume that was 3. So for the 4, when we pop it from the tree, from the queue, we actually find out that this element has the same value as the head. So we can start our trajectory on the downward pass. So we say, okay, next list is the head next, right? And then we check until it's null pointer. So if we have just one element in the list and we match, we basically never enter this cycle, and we just, okay, it's next list is null pointer, we return true. Okay, we're done. If no, like in this case is 4 to 8, and again, let's assume that in binary tree we have 7 here, so it doesn't match for debugging purpose. So what do? We check, okay, do we have left? Yes, let's say this is left, right? Does left value matches next list value, and next list is the next element of the 4, which is 2. So 2, does it match the left value? Yes. So then the next list is 2, not 4, 2 now. Oh, it was 2. So the next element will be 8, right? And the next 3 right, because we match on the left, will be pushed back to the queue. Ah. So the trick is, here's the mistake. We assume, so we never check the right element, but what if we have another 2, 8 here, right? And this is 2, 7. So we wait 2, 7, we didn't find the pass, and we put 2 here, but we never return back to 4, right? So from 4, so it's combination of breadth first search and depth first search. So I would assume this one needs to be breadth first search. So let me redo this. So this part and this part are great. So now let's have depth first search algorithm here to traverse private. It's a bool. It's a pass check downward path, right? Check downward pass. Let's assume we have the same thing here. And root, right? So we already know that the head is equal to the root value, right? What we say is you basically return check downward pass or another check downward pass, right? Here we say its head next and root left, right? Here we say the right now if head equals now PTR, right, we return true, else if, let's say, head value, let's say this thing, like we said exactly. So we say root, not root, and so root is not now ptr, and head value is equal to root value, right? It shouldn't be, oh, we can just access value directly. Why we need this? I don't understand. Value, right? We return, we check for the next one. Else, we return false, right? Now, the problem is what we add to the queue after all right? So, and I would imagine that we have this queue of 3 node, which we, let's say it's by reference, so we have queue. Every time we have queue here and queue here. So, okay, we know that we can't go anywhere from now, right? And only in this case we add something to the queue, right? So, and basically what we do is this, right? If queue, you don't need now left, right, it doesn't matter. If queue not, queue got root, we push to the queue this root. So basically, wherever, every time we encounter the node that is not of our interest, or that it doesn't match, right? Like in this case, we hit 2, right? It matches. Then let's assume we have 1 and 3 here. We call it with left, which is 1, and we call it with 3, which is right. So in both cases, head, which is next element, will be 8. It's not now. All right, so we do not return true. I think we need to have something like this. All right. Then we check, okay, root of the tree, because we call it with 1, is also not now. And those values are not equal, so we don't enter this one. So we go here. Then we say, okay, 1 is not now, push it to the queue, and return false, right? So, what do we do here? Simple. All we do is this now, right? So if check downward pass, we say next tree, and head, right? So basically we sorry, it's vice versa. Head and next tree. So basically here we check quickly that head is not now PTR, which is obviously at the beginning is not now. So we check the root next tree is not null, and I would imagine it's not null because it was added to the queue. Like the root is not null. If it's null, then basically we return false, nothing will be added, and that's it. Wait a second. So if there is no matching download path from here, so I have a feeling that we don't need this. So here is the reason why. Let's assume we started with 1 and this is 4, right? We popped 1, this is 4. This doesn't help, so we put what, 1 back to the queue. No, we still need it. All right. And let's see this. Reverse list if this, and obviously we need queue here as well. Then we return true. Right. And here we just check that next tree value equals to head value. We don't need this. So they're already equal, so we can start matching, right? So we can say head next, so we save a little bit, we don't need to redo these twice. And next tree, because it's either left or right, so yeah, whatever. So we know they're matching, so basically root is not now obviously, and value is matching here, right? So we know this already. So this will be check this or check this, basically. Or we can do or, right? So we can say head next, next tree, let's say left, or this thing, but for the right element, right? So either left or right matches next. All right, if it doesn't match with the value, then we push both left and right. Yeah, I don't know, maybe still too much of the code. It still can be simplified here and there. But okay, let's see. So how much time we spent already? Like, oh, about 30 minutes plus. So let's run the code, debug it, and see if it's passes our check. No, it's not. Man, this is hurts. Let's see this, see out. So we say list, and this is what? Head value, and then tree. And so we do understand what's in this thing. Root value, and done. Oh, we never enter it. Interesting. No, so we should add this one, right? I wonder why it stopped here. So 3 left, not. So it's basically you should check not now PTR. If I understand correctly, right? Let me check. PTR. It's weird, but whatever. And writes 1 again. We didn't get it. 3 not. Alright, now it works. So the problem was with the pointers for some reason. I still don't understand why it's 1, 1 at the beginning. We start with 1, then we hit 4, right? No, I think it's doing something wrong. Because I said a root here. It should be next 3, of course. Looks like it works. Okay, so we hit 1, obviously nothing here. Then we hit 4, then we say okay. We go to DFS now, so we check 2 because it's the only one. Alright, 3, 2, nothing. Then we go to this 4. It's a 2, 8, blah blah blah. Fizz not, and let's also add here just one last check. Queue size, right? Just to make sure we put all elements when it's needed to the queue. So it's 0. So at 4, when we started with 4, right, we have and we popped element which is 4 here, we still have another element in the queue which is this 4. Then we run DFS, these 2, and we ended up nowhere because 2 has nothing, so we put 1 to the queue. So we have 2 elements, 4 and 1. Then when we pop up the 4, we still have 1 element, and this is correct. All right, so seems like it works. Let's see if we can pass all of the checks. Submit. No. Interesting. So we still have time to debug, right? Yes, we have a little bit of time to debug, so let's see why not. So we have 2, 2, 2 and 1. We have 2, 2 and 1, right? This is a good example. I know why. So when we started DFS at 2, right? We put only this element. We didn't put this element. This is interesting. It basically means we still may want to put, so we don't need queue here basically. We anyway put 2 elements to the queue. So then the worst case scenario, so every node in the queue will be traversed at most 2 times in this case, right? All right, so I see. Right, let's then do what we should do. So we don't need this else statement. No, we do need this else statement. We don't need to put anything through the queue here. We just say return false. And let's assume we don't need this thing, right? So we can just comment this thing out. So then, obviously we don't need this, and we don't need this, because we always add elements here. And all we need to say is, obviously we also don't need queue here, so we can comment this out. And similarly here. All right, so run the code. Still should work, but now more elements will be in the queue. Oh, yes, correct. We don't have no. And same here. All right, roughly the same. So let's see. Now we should pass this test. Because every time we're gonna add these 2 to the queue, so if it doesn't fail, so we start again with 2 and then we match it. All right. Done. Under 40 minutes. Maybe minus something for debugging, but that's okay. So right, just breadth first search with depth first search combination works easy. Yeah, because we don't have time to improve memory or time complexity, so let's just submit few more times to get maximum score we can get with from the current algorithm. Memory slightly better, runtime slightly worse. That's okay. And we don't change the state, so technically we can try to use const pointers here. I don't think if it changes anything, yeah, most likely it won't change anything. So all right, so the last thing I will do to improve just code visibility. So what I do is this head and this, right? And that's it. And I say this. And then I remove this, right? If it matches, then we return, no, we don't need this one. Then we return true. Otherwise, we basically add these things, right? Otherwise, we just add stuff to the queue. Now it's super simple. I don't know if it still works, so let's remove the queue. We already know we don't need it. So the code looks slightly prettier. Boom, boom. All right. Run this. That's it. Simple code. Let's check one more time if it still works. So if downward pass matching from the head and x3 element, we return true. If not, we just add both kids of this next tree to the queue, if any, and redo this. Run the code should work. Yes, submit, still passes. Yes. Oh, memory is now better because we removed some extra chunks. Interesting. All right, so based on this, I guess we get the best of the best possible worlds. So it's 96. Memory is not that great. Let me rerun it one more time. Maybe we can get 32.3 and the same memory, the same time complexity. No, time complexity is worse now. Dang. One more time. So let's try to get this and this number. All right, I'm done. With 20 milliseconds, 99 scores per time complexity, I'm solved. All right, so let's switch to the whiteboard here, and let's see if it works. So 99, and memory always bad. 16. So altogether is 115, right? Yeah, it's still a little bit aggressive, I don't know. Nope. Let me redo the entire picture. All right. Done. Thanks for being here and see you tomorrow. Bye.